Good morning and Assalamu alaikum. Today we will start 1.3 Periodic Trends in Physical Properties. As you have studied so far that in modern periodic table the elements are arranged in ascending order of their atomic numbers and their classification in groups and periods is based on the similarity in their properties. Yet, due to the gradual increase in the number of protons in the nucleus and electrons in the outer shell, the physical and chemical properties of the elements steadily vary within a group or a period. Here, we study some trends in physical properties. Number 1. Atomic size. A. Atomic radius. Atoms are so powerful that it is impossible to see an atom with a powerful optical microscope. The size of a single atom therefore cannot be directly measured. However, techniques have been developed which can measure the distance between the centers of two bonded atoms of any element. Half of this distance is considered to be the radius of the atom. In the periodic table, the atomic radius increases from top to bottom within a group due to increase in atomic number. This is because of the addition of an extra shell of electrons in each period. In a period, however, as the atomic number increases from left to right, the atomic radius decreases. This gradual decrease in the radius is due to increase in the positive charge in the nucleus. As the positive nuclear charge increases, the negatively charged electrons in the shells are pulled closer to the nucleus. Thus, the size of the outermost shell becomes gradually smaller. This effect is quite remarkable in the elements of longer periods in which D and F subshells are involved. For example, the gradual reduction in the size of lanthanides is significant and called lanthanide contraction. B. Ionic radius. When a neutral atom loses one or more electrons, it becomes a positive ion. The size of the atom is decreased in the process because of two reasons. First, the removal of one or more electrons from the neutral atom usually results in the loss of the outermost shell, and second, the removal of electrons causes an imbalance in the proton-electron ratio due to the greater attraction of the nuclear charge. The remaining electrons of the ion are drawn closer to the nucleus. Thus, a positive ion is always smaller than the neutral atom from which it is derived. The radius of sodium is 157 picometer and the radius of Na positive ion is 95 picometer. On the contrary, a negative ion is always bigger than its parent atom. The reason is that addition of one or more electrons in the shell of a neutral atom enhances repulsion between the electrons, causing the expansion of the shell. Thus, the radius of fluorine atom is 72 picometer and that of the fluoride ion is 136 picometer. In a group of periodic table, similar charged ions increases in the size from top to bottom, whereas within a period, isoelectron positive ions show a decrease in ionic radius from left to right because of increasing nuclear charge. The same trend is observed for the isoelectric electronic negative ions of a period. Ionic size decreases from left to right. The variations in atomic and ionic radii of alkali metals and halogens are shown in figure 1.1 and 1.2. Figure 1.1 is this, in which atomic and ionic radii of alkali metals is shown, and this is also the same one. But this is for the negative one and the previous one was for the positive one. Number 2 is the ionization energy. The ionization energy of an element is the minimum quantity of energy which is required to remove an electron from the outermost shell of its isolated gaseous atoms in its ground state. The ionization energy of sodium is 496 kJ per mole. Na is equals to Na plus E minus. Ionization energy is equals to 496 kJ per mole. Elements with greater number of electrons have more than one values of ionization energy. So for the magnesium, the first ionization value is energy required to remove the first electron, which is equals to 738 kilojoules per mole. And similarly, the second ionization energy value is the energy required to remove the second electron, which is 1451 kilojoule per mole. A. Variation within a group. The factors upon which ionization energy of an atom mainly depends are magnitude of nuclear charge, size of atom, and the shielding effect. The shielding effect is actually the repulsion due to electrons in between the nucleus and the outermost shell. This effect increases as the size of the atom increases due to the addition of an extra shell successively in each period. Hence, more number of electrons shields the nucleus. Going down in a group, the nuclear charge increases, but as the size of the atom and the number of electrons causing the shielding effect also increases, therefore ionization energy decreases from top to bottom. That is why in alkali metals, for example, it is easier to remove an electron from cesium atom than from lithium atom. The change in ionization energy of 1A elements is shown in figure 1.3. Variation across a period. Generally, smaller the atom with greater nuclear charge, more strongly the electrons are bound to the nucleus and hence higher the ionization energy of the atom. By moving from left to right in a period, the outer shell remains the same while the nuclear charge increases effectively. That makes the removal of an electron difficult and hence the value of ionization energy increases. Although the number of electrons also increases in this case, but the shielding is not very effective within the same shell. The trend of ionization energy of short periods is shown in figure 1.4. The figure also reveals that the inert gases have the highest value of ionization energy because due to complete outermost shell in them, the removal of electron is extremely difficult. Number 3. Electron affinity. The electron affinity is the energy released or absorbed when an electron is added to a gaseous atom to from a negative ion. Electron affinity for fluoride ion is minus 337 kJ per mole. Energy is usually released when electronegative elements absorb the first electron, and electroaffinity in such cases is expressed in negative figures as in the case of halogens. When a second electron is added to a uninegative ion, the incoming electron is repelled by the already present negative charge and is absorbed in this process. The absorbed energy is expressed as the electron affinity in positive figures. Electron affinity depends upon the size of the atom, nuclear charge, and vacancies in the outermost shell. Relatively smaller atoms with one or two vacancies in the outermost shell show large values of electron affinity. Electron affinity generally increases with increasing atomic number within a period and decreases from lighter to heavier metals in a given group of the periodic table. Knowledge of electron affinities can be combined with the knowledge of ionization energies to predict which atoms can easily lose electrons and which can accept electrons more readily. Metallic and non-metallic character. Number 4. It has already been discussed in these chapters that the elements of periodic table can be divided into metals, non-metals, and metalloids. Chemically, all the elements have a tendency to form positive ions. By losing electrons are considered metals. All metals are good conductors of heat and electricity. A characteristic property of metals is that they form basic oxides which give bases when dissolved in water. Na2O plus H2O is NaOH. As it becomes easier to remove the electron of an atom bigger in size, therefore metallic character increases from top to bottom in a given group of elements. On the contrary, it decreases from left to right across a period. The element of group 7A, the halogens, are least metallic in nature. The elements which gain electrons and form negative ions are called nonmetals. All the gases are nonmetals. The nonmetals are normally poor conductor of heat and electricity. Nonmetals form acidic oxides which yield acids on dissolving in water, just like SO3 plus H2O is H2SO4. Non-metallic character of an element decreases as the atomic size increases. Therefore, in a group of non-metal like halogens, the non-metallic character decreases from top to bottom. The member at the top, fluorine, is the most non-metallic element of the periodic table. This trend can also be verified in elements of group 5A and 6A. Nitrogen and oxygen are pure nonmetals and usually exist in gaseous state, while bismuth and polonium, the members at the bottom of these groups, are fairly metallic in nature. We'll continue in the next part.